Okay, thank you. Thank you for the nice introduction. And hello, everyone. It's a great honor to share my research about secure learning adversarial environment here with everyone. So I think I have recently given talks at CMU about game theoretical analysis to model the interaction between attacker and defender and improve the robustness, or some specific attacks in 3D, 2D, something. And in this talk, I want to talk about something slightly different with emphasis on the defense side. But still, I will give, in case some of you are not exactly familiar with attacks. So we will motivated with some existing attacks and see what could happens in real world and how severe some adversarial attacks against the machine learning systems could lead to. And then we will mainly focus on some of our recent research about using knowledge inference to improve the robustness of machine learning systems. So overall, we can see that machine learning has been ubiquitous in the world. It has been applied to different domains to help make our life better. For example, autonomous driving, intelligent medical treatment, smart city, etc. And also in many security critical areas, for example, malware classification, fraud detection, autonomous driving. So all this machine learning has played a very important role. But we can see that even though those powerful AI learning algorithms have been helping a lot, there are a lot of security and privacy concerns brought by such techniques as well. For example, in real world, like in 2016, the White House associated Twitter account was hacked via phishing emails and spread the rumor that the White House has been attacked, which triggers the autonomous trading bot to dump a large amount of stocks within seconds. And this swipe about 136 billion with seconds. So this is like happening in real world, and it's indeed kind of attacks in NLP, in fake news, and to human, such news will be easily filtered, but for machine learning models, it's hard, and it can lead to, you can see some severe consequences. And similarly, from the privacy side, say the Australia airport has using the biometric recognitions as the safety screening, which has raised a lot of concerns for, say, personal information leakage, misuse, and say medical insurance misuse, etc. And as a side information, actually, because of the information leakage of individuals, and every year, I think in the US, the medical insurance misuse has been causing tens of billions of dollars loss. So that is to say, even though we are living in a very friendly environment with machine learning, for example, we have all kinds of convenient platforms to help us develop machine learning tools, training our models, test it, debug it, evaluate it, but we are still living in a very adversarial environment. Therefore, a typical machine learner still have a very hard life to develop the so-called secure, trustworthy, private machine learning models. So that's why we need to look at or try to understand different types of adversarial behaviors and adversarial attacks, and therefore develop the robust or secure machine learning pipelines with understanding about the limitations or capabilities of attackers. So with these types of like real world examples, one quick question you may want to ask is, what's exactly adversarial, right? So what's the fundamental causality of such abnormal behaviors, and why machine learning models are kind of vulnerable? So from the first principle, we can see in traditional machine learning approaches, we usually assume the training and testing data are drawn from similar or even the same distribution, right? Therefore, we can do like a training on one data set and trying to make inference on the rest. However, in the adversarial environment, either the training or the testing distribution can be manipulated. For example, if the training data is manipulated, it's usually called poisoning, or specifically to deep neural networks, there are backdoors and these types of attacks. And these types of attacks could be very realistic. For example, in Netflix, in Yelp reviews, you can create some fake accounts and affect the recommendation or affect the final reviews of those systems, right? And if the attacker can manipulate the test data, meaning that your model is well trained, it's clean, everything is good, but during testing time, the attacker can manipulate their instance before sending to the machine learning model, then this is called evasion attack. And these types of attack can happen even more often in real world, because as you can see, we can train a good model and protect it, but there is no control for us to constrain that what's the test data, where is the data come from, right? So in this case, in this talk, we'll mainly focus on the evasion attack. And for poisoning attack, there are many literatures and related work, but if you are interested, we can discuss later. And we'll focus on, in the terms of the evasion attacks, what's the attack look like in practice, and what's the potential way to defend against them. And one quick example from the real world case is this adversarial stop sign. I hope many of you have seen such attacks, and I think especially this picture have been cited in many places to demonstrate, okay, machine learning is vulnerable and we should be careful and trying to improve the trustworthiness of machine learning models, right? So basically, I will not go to detail about how this attack is generated, but essentially it is trying to use optimization types of method to find the spatial vulnerable regions, and then trying to use some smooth loss to generate the perturbation within certain regions. And surprisingly, it works in the sense that it can generate the spatial constraint perturbation. And more interestingly is that for these types of perturbation, it works under different physical conditions, which is slightly harder than a digital perturbation, which you can directly send the manipulated pixels to the machine learning models, right? So for example, here, each column shows different types of perturbation. Each row shows different physical conditions, including different distances, angles, lightning, etc. And you can see here is all the stop signs in these slides, although for humans, they are still like stop sign, but they are misrecognized as speed limit sign 45, which is called the targeted attack with a specific adversarial target, which you can see this can lead to severe consequences if the car will not stop at such sign, right? And the right-hand side specifically here are misrecognized as the stop sign, meaning you will suddenly stop at it. So this shows that indeed, either these types of letters or kind of like fading out, or even just a white and black stickers. Just one thing to mention more, since actually a lot of people are curious about why this color only is generated as white and black. That is not on purpose. It's like after optimization, it shows that even such simple enough perturbation is enough to attack such signs, but the position itself is very important. For example, if you move this black sticker to the below it or things, it won't work well, because the vulnerable regions is very important to identify in such attack. So this is just an example as a motivation to let you know, indeed in real world case, for example, such physical attacks is possible, and it can fool different types of machine learning models. For example, we can see a real-world case that we can drive autonomous driving vehicle towards this stop sign. On the left-hand side, it's a perturbed sign we just seen, and on the right-hand side is a controlled vanilla stop sign. And we can see from the caption here, okay, what happened? From the caption here, on the left-hand side, this perturbed sign is consistently misrecognized as the speed limit sign 45. But on the right-hand side, it's the control environment is always stop sign. And this is true with different angles and distance, like when the car driving towards it. So after this attack, several people ask, like, what if in real world, say, autonomous driving industry, people use sensor fusions, including both cameras, lidars, radars, etc. And focus on this specific example, we can see or let you know that it is still possible to attack machine learning models, including lidar and other sensors, as a joint fusion sensor system to generate, say, here is a like 3D object rather than a kind of like a planar object such as the stop sign. And you can see there are some more simulation examples here, but let's look at a real world example to get some sense. So basically, you can see here is the real also 3D objects, which is 3D printed. And you can see when the car driving towards it, even though there is an object and there is no LiDAR detection here. However, on the above one, this is a control experiment with a box with a similar size. And you can see there is always a green box here, shows the LiDAR actually can detect this object. That means with this obstacle clearly here, if the shape is optimized in certain way, then the car actually cannot see this object and can hit into it. So this will again lead to a concern about if our machine learning models and detections, recognitions are vulnerable against the adversarial objects, adversarial a lot of other related work talk about adversarial stickers like t-shirts or something else. And this leads us to focus on the main question we want to ask today is about what's the potential way to improve the robustness against such attacks, right? How can we develop more trustworthiness and more secure systems? So as a quick summary, actually in current literatures, there are many defense or detection methods have been proposed against such potential adversarial attacks or behaviors. For example, since 2014, there are different types of detections, defenses, trying to use robust statistics to filter out outliers, to identify malicious behaviors, to do ensemble, to do adversarial training, to pre-processing, post-processing, etc. But again, this line of literature about empirical-based robust training and robust learning methods have been later on shown vulnerable again to the adaptive attackers, meaning that if you, as an attacker, if you tell me that what defense or detection method you are trying to use, it is possible for me to adaptively attack the model again. So this becomes a kind of like a cat and mouse game. And one potential solution to it is maybe we can form it as a stackable game, right? Which is the two-step game. So some of my previous talk about how we can model a stackable game for the interaction between attacker and defender, and we can eventually solve it. But the limitation for the game theoretical analysis is that usually solving the game is quite expensive because you need to form the game as certain constraint optimization and need some linear solvers or mixed integer form it as a mixed integer linear program and solve it. So it's relatively hard to scale up to very large scale systems, right? And again, these types of empirical-based attack defenses are not enough to provide the confidence about how secure or how robust the model is. Therefore, after these types of literatures, there is a big branch. Maybe some details you cannot see here, but overall, we only want to look at these three boxes here. So basically, there are line of literatures about certified and verifiable robustness, and a lot of good work from SAMU and Zico's group and many group, I think. And here we summarize it a little bit about this line of literatures, and you can see there are mainly two big branches. One is the deterministic approaches, which you can formulate the robustness of machine learning models as a constraint optimization with the objective function as minimizing the loss, of course, and the constraint as certain constraints that the attacker need to satisfy. For example, the magnitude of perturbation, the special machine learning model, for example, sigmoid properties, or different types of machine learning model properties. And with these deterministic approaches, it's good that meaning if the model tells you, or if the verification tells you this instance can be certified, it means it indeed can be certified, otherwise it can not. So it includes both complete verification and incomplete. Incomplete means that if an instance is told that it cannot be certified, it doesn't mean it is necessary to be unsecure, unsafe. It could be that the method just is not powerful enough to verify this instance. However, all the these branches, since it's constrained optimization, so there are different ways to solve them based on optimization approaches. For example, different linear relaxation, different nonlinear relaxation, or all kinds of approximation method. But you can see because of the constrained optimization, as we mentioned before, this branch could be very expensive to solve. Therefore, this branch method cannot exactly scale up to, for example, ImageNet level of dataset. And as a result, there's a new branch come out in terms of the verification and certified robustness, which is the probabilistic-based approaches. And corresponding to this, there is a line of literature as a variations of the key technique here, which is called the randomized smoothing. And for this line of this branch, all the method can be scaled up to, say, ImageNet scale types of data, given their probabilistic nature. And we can see, okay, that's good, because here we can have better certification with more confidence about how robust the model is, rather than testing without any guarantees yet, right? However, again, as we introduced before, the limitation for this whole line research here is still limited to a small radius of perturbation. So if we want to certify certify the model's robustness against a powerful attacker, saying the attacker can do larger magnitude of perturbation, and the whole literature here will give there is still a big gap between the certified robustness and the actual benign accuracy. That means inside this gap, there is still a lot of things we can do to improve the certified robustness with various maybe additional information or additional analysis. And that leads to the main topics or the discussion we want to discuss today is about whether we can leverage additional information outside, say, the machine learning model, outside the data set itself, to help improve the robustness of machine learning models. For example, most of the statistical machine learning models now focus on or use a pure data-driven approach, right? And we know that a lot of information are not exactly modeled by data itself. For example, as all the examples we've seen before, human cannot be fooled, right? But only machine learning can be easily fooled. And with human, we can imagine, of course, we have our experience, we have our logical inference abilities, we have our domain knowledge, different types of things. So that leads to the question that whether we can incorporate our inference or logical thinking abilities to the machine learning model or pipeline, therefore to make it capable against such adversarial behaviors in real world. And by injecting such extraordinary information, we slightly categorize such information as intrinsic and extrinsic. So intrinsic means that some inherent information from the data or model itself. For example, we know semantic segmentation has spatial continuity, and the video and the say audio data have temporal consistency. So based on those properties, we actually can show if you want to perform the attack by still maintaining the spatial consistency and temporal consistency, etc. It's very hard. Therefore, we can leverage such information to defend or detect adversarial behaviors, because once the perturbation is added, such consistency information would be broken and very hard to fix by the attackers. And another type is extrinsic information, which is more interesting in the sense that, for example, it's domain knowledge, right? We know some domain knowledge that stop sign should be of red color, it should be of octagon shape. How can we enforce such knowledge to the machine learning pipeline learning process to enforce the learning model to recognize such knowledge and be relatively more robust against attacks, right? So this is one example of these types of dream by incorporating knowledge to machine learning system or pipelines. So basically, we build up one machine learning pipeline called sensing and reasoning. And the sensing here is still based on statistical machine learning models. For example, all the neural networks, and they can in charge of different types of tasks. For example, the first one trying to classify whether this is a dog, whether this is a cat, whether this is an animal, etc. And later on, all the output can be formed as an input of a reasoning component. And in this reasoning component, it can be realized by some probabilistic graphical models, for example, Markov logic nets, Bayesian nets, or other statistical graphical models. And therefore, with these graphical models, we can embed the knowledge we have, the knowledge link we have. For example, cat belongs to an animal, so that there is like a factor here connecting these two output, right? And the goal is to certify the end-to-end robustness of this whole pipeline. And the hope is that either the hope or the intuition is that you can imagine it would be very hard for the attacker to attack this whole system, because if the attacker can attack all the sensors and still maintaining the sensor's logic, meaning if I attack this to say a stop sign, I should attack this to a road sign as well, because only stop sign belong to road sign. If I cannot attack this one, then I can recognize there is some conflictions or violations for the rules here in the inference time, in the reasoning time. Right, so this way it makes the attack even harder, and later on we can see how such hardness can be reflected. And here the basic goal is that given the input perturbation similar with all the certification for machine learning, so given the input perturbation magnitude eta bounded by some CI, and we can use the traditional robust verification method to get the output bound, right? Bounded by, say, CS. And given this information, whether we can essentially solve the min-max in the reasoning component such that we can bound the final marginal probability with CE, so that this CE will be our end-to-end certification bound for robustness, right? So hopefully this is clear. But before we can talk about how we can address it, there are some obstacles, or this is a formal definition of our certified bound, basically given this E representing the whole system, and basically given the query and the alpha and alpha prime representing the benign and adversarial distributions, and given data drawn from these two distributions, what's the expected difference in terms of the final probability, marginal probability bound. And one challenge, of course, for this system is that we know for traditional graphical models, say Markov logic nets or things, the inference would be sharply complete, right? So given this complexity, it would be very hard for us to actually exactly solve the end-to-end machine learning pipeline, right? Of course. But on the other side, we can see there is also additional opportunities brought by such graphical models, because usually they can define a more structured, say, a probabilistic distribution in the exponential family, or with more function structures, say the output of the each like factors is a probability, so it's non-negative, so it can maintain some monotonicity properties, and therefore we can solve the min-max problem for this graphical model part or reasoning part. Because just a quick background is that eventually whenever we want to certify the machine learning component, we are aiming to solve a min-max problem, right? The mean over the theta of this component, parameters of this component, and max over the perturbation magnitude, meaning we want to certify under the worst case, which is the max part, the minimal loss that can be achieved by this machine learning component, right? So we can imagine this min-max is hard in traditional deep neural networks because it's non-convexity and non-linearity, but with these types of graphical models, although the inference time is like sharply complete, but there are additional opportunities we can leverage. And with that, we can see it is possible. We can see how the system can be really built up, and then we'll introduce what's like a certification result we can obtain. So basically, take the previous examples, we can see every neural network will map the input to a probability output here, and then connect with the reasoning component, which the R here representing the reasoning, and taking all the probability as the input, and based on some knowledge base to build up these connections. And such knowledge could be, say, one image. If one image is classified as a dog, it must be an animal, right? These types of information. And then we can map these types of knowledge into a Markov, like a first order logics, and then we can embed the first order logics into the MLN program. So basically there is a composition definition for the robustness for different component. That means if you can improve the robustness certification for each component, you can also improve the end-to-end certification. And that's why we want to focus on this part to see how tight we can certify the robustness for the graphical reasoning component. And here is a more concrete example you can see with different sensors. And there is some factors saying if it's C predicted as dog, it should belong to animal. And similar, if it's a cat, it should belong to an animal. And there are two types of the sensors we can get here. One is the interface types of factors, which adds the interface component of between the sensor and the reasoning. One is interreal factors, and we can train or generate the weights for these types of factors. And for the interface factors, the weights will just be log out, and we will see later why this is defined as a weights. And for other interreal factors, we will train this program and get the weights. And the nice thing for this is that in terms of training it, we actually don't need do not need the input data, because here you can see all the input is some probability. You can even sample with your confidence or some prior knowledge. You can even sample, say, I think this, like I care about whether this sensor is robust or not. Therefore, I can I can sample a large deviation of the prediction here to simulate that this sensor is attacked, right? And under this case, I will train this program and obtain like the weights here. This means we actually don't even need to simulate a lot of attacks, which save a lot of budget, because otherwise we need to ask a question, what types of attacks to generate and how much perturbation we add, etc., right? Compared with traditional adversarial training. And what you can see here is that in terms of the final certification, what we can get is simply the probability given Z1 divided by Z2, and Z1 representing all the grounded possible word, and Z2 representing all the possible word, meaning all the different assignment for this like MLN program. And the Z1 indicate when the grounding is true, basically when the logic is satisfied, how many, what's the probability of it. So basically you can see when upper and lower bound this probability itself, we will be able to get the final certification of the end-to-end robustness certification. And concretely, we can see, as we mentioned before, how hard this question could be. So I think maybe some of you have the background knowledge about a counting problem, which is essentially trying to find a constant such that satisfy this inequality given a weight function and a query function. And itself is Sharpie complete for the counting problem itself. And for the robustness problem, as we defined before, we can write it as a way similar with this format, meaning with a weight function, which is a weight for the graphical model, and the query function, which is a reasoning component with expectation computing. And we alpha and alpha prime representing two distributions, which are benign and adversary, and we want to bound their like difference, which is the marginal probability distance. And we can see it is possible to reduce the counting problem to the robustness problem we care about, actually. And this is actually unfortunate thing, meaning that this robustness itself would be Sharpie complete, and meaning like, for example, for MLN, take the example, certifying such robustness itself would be of high complexity. And similarly, this result can be generalized to Bayesian networks with special structure, for example, tree structures. And even though this is hard, but we can ask a question is, although we know there are a lot of literatures currently giving some approximations for the inference for graphical models, right? Like embed as GN networks and use variational inference or some Bayesian inference to give the inference for the reasoning component or for the graphical model inference. Basically is our reasoning component here. And then the question is, if we can assume we have an oracle that we can query to get the inference, right? Then how hard the robustness inference itself would be. So basically this gives a very promising result, as you can see, is that based on the good properties we mentioned before, in the graphical models, the output is like non-negative, therefore preserve some monotonicity properties. And we can see if like we can represent the like oracle inference of the Z, which is the inference of the graphical model, as a ground truth plus some noise with a lambda parameter, right? And we can see if the lambda actually is larger than 1, basically this is what we want, right? If we want to get the max, of course, we can take the max and the mean here. And on the other side, if we want to get the mean, we can change it. And if we want to solve it, we can see, we can leverage the oracle inference as the input here. And therefore, we can obtain that if lambda is less than 0, and we can have proof the monotonicity of this inference. And therefore, we can see because of the monotonicity, we know the mean and max will be chosen at the boundary C. C is the like the magnitude of the perturbation or the input of the graphical model part. Like what's the largest change as the input, C and minus C. And on the other hand, if lambda is smaller than -1, similarly, it will monotonically decreasing. So again, we will select the 2 extreme cases at the 2 points. And if lambda is between -1 and 0, then there is a nice, it's not monotone anymore, but there is a nice property for it is the convexity. And then therefore we can use 0 order to find the optimal like position here and still to address this whole mean and max. Therefore, we can get the upper and lower bound for the marginal probability that we want to prove or want to certify. So let me know if there are any questions. I think the whole logic here is clear in the sense that we want to use graphical model component as a reasoning component to help make the inference, and the graphical model itself have some good properties. With access to the oracle of their inference, we can directly calculate the upper lower bound of it, and therefore to model the range of the marginal probability of the final output prediction probability. And this is nice because this means that we can get the end-to-end certification for this whole machine learning sensing reasoning pipeline. And we can see these types of results can be generalized to Bayesian networks and other types of graphical models with specific structures. And let's look at the example concretely, how this can be realized and how such knowledge can be helpful and how helpful it could be, right? So one example is this, we call it a primate net. So there are 2 types of knowledge here, very simple. One is a hierarchy. Basically, if you are great at pay, you must belong to a pay, right? This is a hierarchy between the children and the father. And there is types of exclusive knowledge, meaning if you are great at pay, you should not be less at pay because they are on the same levels, right? So basically, these 2 types of knowledge can be represented as a first order logic like this way. And we can incorporate into a Markov logic net and train the model. And here we can first see, compare with like a single or ensemble machine learning models with several neural networks, which is called without knowledge. And with this composition of the pipeline, it is called with knowledge. We can see even the benign accuracy increases a little bit. And this is quite surprising at the beginning, because we all know there should be a trade-off between robustness and benign accuracy, right? There's the no free lunch theory. But with knowledge, actually benign accuracy improves, which also makes sense because we incorporate or introduce new additional information. So now the trade-off no longer applies, and with additional information, you can achieve additional things. For example, benign accuracy improve slightly. And of course, in terms of robustness, which is our main goal here, you can see the certified robustness actually increases like significantly from 0.8 to compared with 0.5, which is a standard traditional state-of-art certification for a single neural network. By incorporating with the knowledge, you can see alpha here means how many percentage of the sensors you want to attack, for example, 10%, or even 50% means half of the sensors are like adversarially attacked. And the certified ratio, actually, or certified robustness is still quite high, around like 80 or 60%. And with this certified ratio, we actually want to know how confident those robustness are. For example, we know if certified ratio is 90%, it means for 90% of the instances, they can be certified as robust under constraints of attacker. But we want to know how confident they are. For example, if they are here, it means that it can only give a correct prediction with, say, slightly above 0.5 confidence, right? But we want the margin to be as large as possible so that the model can be more confident towards the ground truth. So in this figure, it's quite interesting in the sense that we show on the green background shows the correct class, and the pink shows the wrong class, and the frequency of the bar shows how many instances, and the x-axis shows actually the margin, basically the correct class minus the top wrong class. And you can see towards this end, the confidence is high, and you can see the blue bar is actually quite high on the right-hand side, meaning that with knowledge, it can not only give you robust certification, but also it can very confidently give you the certification. And unfortunately, for some cases, the red bar, which for the without knowledge, is actually very confident to give some wrong predictions. So this is another interesting part that that shows that knowledge would help. And this is based on the example of the primate net, which contain two types of knowledge. And similarly, we can apply this pipeline to different applications. For example, NLP with a stock market news-based prediction, and the knowledge we can use is based on the price increase and decrease. The summarization of the final price should satisfy this increase decrease, right, as an arithmetic rule. Or this, like if the news say the company makes profit, their price should be high in such case. And similarly, we can see either the benign accuracy or the certified accuracy or certified rate is quite high. And compare with confidence, it can sometimes it can be very confidently to bring the wrong prediction or attacked sensors back to the original correct class, because with the knowledge, it can help to correct the mistaken or misled the sensors here. And next, I think I can use 1 or 2 minutes to quickly introduce another interesting pipeline very connected with this. Basically, the question is, the sensor reasoning we introduced is very interesting in the sense that every sensor in charge of a small task, right? And another question may come from this framework is, what if I have a main sensor, right? My main sensor want to do say a main task, and can I leverage some auxiliary sensors to help with my main sensors benign accuracy, robustness, etc. And this, similarly, we can build this pipeline in enjoy the similar principle, but will have slightly different additional interesting properties. So we can see as a whole series. So basically you can see, okay, if my task is want to do the road sign classification, right? So there is a main task is the road sign classification. Of course, I can have some auxiliary sensor to detect its shape, detect its color, detect all these things. And actually also people ask this question, like in the attack we saw before, why the machine learning model not focus on the shape or colors to recognize it, because human can do that, right? But the question is, what's the principled way to recognize shapes and colors and help joint inference, right? So this is one example of such principled way to incorporate such knowledge. And here we have two types of knowledge. One is permissive, one is preventive, which means that if you identify there is a stop pattern, it will always indicate it is a stop sign. So the auxiliary sensor indicates the main sensor's output. All the others, like knowledge is on the other way around. Basically, if I detect the main sensor tells me it's a stop sign, it should be of octagon shape. It should not be other shape, right? And these two types of directions of knowledge will help us to formulate this knowledge and build up, say, Markov logic network, or just a conditional random field here. So basically, there are two types of results we can get in addition to the result we see before. And basically, it shows that compare the main sensor and the auxiliary sensors, we can lower bound the accuracy of the whole pipeline, which is what we want, right? And the lower bound actually shows non-trivial lower bound of the accuracy under the constraint of this mu actually representing the contribution of different sensors. And the high level intuition itself is actually quite direct, meaning that if the contribution of like auxiliary sensors is non-zero, then the auxiliary sensor, the main pipeline will definitely be better than auxiliary sensors, right? Either we can lower bound the main pipeline's accuracy, or as a proposition, we can, by the way, show the main pipeline will always be better than the main sensor. Yeah, and how to derive this contribution of different sensors is based on we can use some tailbound to find the optimal weights for the graphical model part. And based on these optimal weights, then we can easily show the contribution of each component and show in the end-to-end pipeline what's the lower bound of their accuracy. And interestingly, as we mentioned before, because these types of machine learning pipeline is agnostic to different types of attacks, right? Because when you train the reasoning component, you don't need to consider what attack to use, right? So this pipeline can be tested against arbitrary attacks. So that's one thing like more interesting and advanced than, say, adversarial training, which you need to focus on what types of attacks you need to generate, right? And you can see, compare the main sensor and the pipeline. Surprisingly, the pipeline will be better than the main sensor under different types of main sensors. And this, the access from 1 to 46 actually is index of different attacks, including physical attacks that we have seen before as a stop sign, different LP bounded attacks, white box, black box, and some common corruptions, and some unforeseen attacks. For example, the common corruption including fog, JPEG, etc. So like you name it, right? Whatever attacks you can think of, it's possible to test against this pipeline because it's attack agnostic. And the bar here shows the improvement of this compared with the corresponding state of art method for the specific types of attack machine learning models. And a concrete example you can see is that, for example, against a physical attack, against the state of art is adversarial training, or DOA is kind of patch-based adversarial training claiming to achieve good performance. And we can see, compare with pipeline here, the green means the improvement compared with the corresponding main sensor. So basically, the pipeline here incorporate each state of art defense model into the pipeline as a main sensor and incorporate the reasoning component, and therefore get the final result. And we can see for each pipeline compared with the corresponding main sensor, the improvement is quite significant. And this is true for different like LP, like some white box unforcing attacks like snow, fog. Basically, we look at the color here, all the green shows the improvement. And for benign accuracy, sometimes there is small decreasing. And for robustness under different types of attacks, it's always have non-trivial improvement, and under some common corruptions, similar phenomenon. So we can see indeed the security and the privacy problems are common and very concerning for different machine learning paradigms, and only rely on data may not be enough for current statistical machine learning models. We may want to incorporate additional extraordinary information, either intrinsic or extrinsic, to help the inference to make the model or machine learning pipeline more trustworthy, right? And domain knowledge is one type of thing, and there are other questions like what types of knowledge is robust. Yeah, you can imagine there are bad knowledge as well, right? And what types of method we can use to further scale up this whole pipeline to large scale like inference, etc. So I think these are the future interesting questions for these types of robust machine learning pipeline. Okay, with that, that's my talk today. Thank you, everyone. So let me know if there are any questions.
All right. Thank you, Bo.
Thank you.
All right. Is there any questions from the audience? Comments, feedbacks? Well, I do have a question. Not me, actually. Like a friend of mine who already left early because of a meeting. So I think his question is like, this seems to have a flavor of the symbolic AI thing where, when you deal with the first order logic, but how easy it is usually in your data set to gather these kind of relationships. Don't they require a lot of manual inputs in terms of the relationship?
Exactly. That's a very good question in the sense that indeed gathering the knowledge would be expensive, and actually that's also what traditional AI is trying to do, right? Before the 90s, and we're trying to use different knowledge expert systems to help do the inference, but it's not so successful compared with deep neural network currently, right? And the good thing for these types of pipeline is, remember, we're not using knowledge to exactly do inference. We still leverage deep neural networks. However, the knowledge is just trying to find the violations. That is to say, we don't need to have a comprehensive knowledge. We only need a small set of knowledge. It's enough usually to find the violations. For example, in the stop sign example, we just need very simple knowledge in the sense that if the shape is if we only use shape to detect road signs, it definitely will be very inaccurate. But here we use, deep neural networks, so the accuracy is guaranteed here. But if there is no violations, the accuracy will be just reduced to the accuracy of neural networks. That's great. However, if there is violations, then because the neural network itself is very easy to be attacked, although it is accurate under benign cases, then the violation could easily identify, say, okay, there's something wrong and we should correct it. So that's why this pipeline can be enjoy both the advantage of deep neural networks, good representation, and the knowledge inference. And in particular, about how hard to get this knowledge, because we don't need a comprehensive knowledge, then you can see it's relatively easy because we only need 1 or 2 types of rules. Usually it's enough to identify the inconsistency. But it's indeed like data set dependent. For example, it's roadside, it's animal, it's like NLP. We need some manual work to identify 1 or 2 rules, but we don't need all the rules. Yeah.
Got it. Yep. Thank you. I actually have another question, but actually for myself this time. Yeah, so this is like in general, because I think, for instance, from the theorems, it seems that these are still like perturbation-based attacks, right? But in general, do you think these kind of relational, like extrinsic knowledge will help when you consider like more general, adversarial attacks in the more general sense, where not just perturbations, but like, you know, rotations, or I don't know, like, is there if there's a basis of adversarial attacks, like, you know, this is a infinite dimensional space, like, will they help in that space as well?
Yeah, that's a good question. So I think you asked in theory, yeah, it's hard. For in practice, like empirically, for example, there's common corruptions or anything, we can see it improve robustness. But in theory, in terms of the end-to-end certification bound the marginal probability, it's not necessary to be based on LP bounded perturbation, but it's indeed need to bound certain perturbation in the sense that, for example, here, we need to know the prediction of the neural network here, how like what's the upper lower bound for their prediction probability. So the input attack, either it's LP, it's semantic transformation, it's whatever attack, that's fine. But we need to know under this potential attacks, what's the upper lower bound probability here. If you tell me this thing could say range from 0 to 1, indeed the final prediction, like final certification of the reasoning component is hard. But if we are confident to know something about this prediction probability of a single neural network here, say, I know there's under certain attack, this model will give me from 0.6 to 0.9. And then with that range, this end-to-end certification is possible. Yeah, that's the essential part for the prediction probability bound given each single sensors.
Right.
That is required for the end-to-end certification.
Right. Yeah. Okay. Yeah, makes sense.
Yeah, I think there are a lot of work to do along this line, but indeed it's very related with causal, because causal can be a part of knowledge here. It's related with neurosymbolics, but neurosymbolics actually have the neural as well, but here will be pure graphical models. Yeah, and how to automatically generate knowledge, although existing, like in the world currently, there are so many ready to use knowledge base that is also possible. But I think one main question is how to like scale this up to like lots of knowledge, and because the inference time is indeed complex, so how to scale that up would be an interesting question.
Right. Yeah. Agree. Cool. Other questions from our audience? All right then. Okay, let's give our speaker another round of applause, I guess. I know people already, you know, clicked applause already. Okay. Yeah, I think eventually a lot. Well, thank you, Nathan. Yeah. All right. Well, let's thank Bo again for this amazing talk. As a reminder, we're meeting again next.